Hello everyone, we are going to commence this month's webinar conducted by Institute of Physics Sri Lanka. I'm Shant Gamage, President of IPSL. The main objective of the IPSL is to promote and advance the science of physics in Sri Lanka. If you visit our webpage www.ipsl.lk, you will be able to get more information about our activities. We have been organizing this webinar series to promote physics and its application and aware the public on 4 key topics related to science. I take this opportunity to thank immediate past president of IPSL, Professor Susira Perra, and last council of IPSL. Professor Susira Perra and last council members initiating this webinar series. Thank you very much, Professor Susira Perra, for your excellent service given to IPSL. Regarding today's presentation, so please mute your microphone and we will give time at the end of the session to ask questions if you have any. Also, during the session, you can type your questions on the chat box so that the moderator can ask your question from the resource person. So before introducing our resource person today, I would like to warmly welcome all the participants of this webinar. Thank you for making the time to watch our seminar today. So today we have invited Dr. Rasika Mohottige from University of New Jersey to speak on the topic self-assembled nanostructure form on silicon surfaces. First of all, let me welcome Dr. Mohottige on behalf of IPSL. We are honored by your presence. Thank you for accepting our invitation. Before formally start the presentation, let me call upon Dr. Chature Nupearachi, co-editor of IPSL and convener of the Committee of Popularization of Physics. Thank you very much, and over to Dr. Chature.
Thank you very much, sir. It's my honor and privilege to welcome our resource person for April webinar. I won't waste much time. So Dr. Rasika N Mohottige obtained his BSc and MPhil from the Open University of Sri Lanka. He moved to USA afterwards and then obtained his PhD from the University of North Dakota. Currently, he's a postdoctoral research associate in Rutgers University at New Jersey. He is also an adjunct assistant professor of physics at City University of New York College of Staten Island. Dr. Rasika is interested in both experimental and theoretical physics. His primary motivation is to make new materials and study their electronic and chemical properties experimentally and theoretically. So as an experimental physicist, he has a strong background in many aspects of operating, scanning, tunneling, microscopy, spectroscopy, low energy electron diffraction, OG electron spectroscopy, X-ray photoelectron spectroscopy, and atomic force microscopy. He's also interested in density functional theory and numerical physics. So I'm really honored to have you, Dr. Rasika. Now the digital platform is yours.
How should I start? Yes, good morning, not good morning, good evening, everyone. So Dr. Chature, thank you very much for your nice introduction about me. And also I should thank Institute of Physics Sri Lanka giving me this opportunity to talk about my research interest and share my research experience among the scientific community in Sri Lanka. Okay, before wasting time, let me go ahead and start my talk. I think everyone already know the topic that I'm going to talk about. I'm going to talk about self-assembled nanostructures formed on silicon surfaces. Okay, let me go ahead and start my talk. So this is the content of my talk. I'm going to talk about motivation of the research, introduction, experimental and methods, and results and discussion, and the conclusion. Actually, this research mainly part of my PhD research that I did at University of North Dakota. So the motivation. So as continuous miniaturization challenges in lithography, techniques in electronics, this self-assembly process become more attractive among the scientific community, especially in nanoscience and nanotechnology. So why are we interested in self-assembly? This process, a spontaneous process. And the main important thing is these self-assembled base process are very cheap, easy, and quick. So what kind of nanostructures available for study? So different research groups in all over the world, they work on different types of nanostructures. Quantum dots, nanowires, clusters, such as string clusters, nanocrystals, nanoisland, you name them, lots of nanostructures. But in this talk, and the nanowires. That's what I worked on during my PhD. Okay, let me go ahead and draw your attention to the introduction of the talk. In this talk, I'm going to focus on silicon 110 surface. There are three types of silicon surfaces available: silicon 111, silicon 001, silicon 110. Today, I'm going to focus on silicon 110 surface, because this surface is very interesting surface because it has a higher Hall mobility, which is very useful in detector applications in electronics. And because this surface has two fault symmetry, and the other two surfaces, silicon 11 and silicon. What is the uniqueness of two-fault symmetry? Because if we grow nanostructures on this surface, we can get the nanostructures in the same direction. That is the important property of this silicon 110 surface. Okay, let me talk about a little bit of silicon surfaces. You can see in the figure 1. This is the bulk, this is the unit cell of bulk silicon. So, and let me introduce what is the silicon 110 surface. This is the side view. This pink color thing, it shows you the silicon actually 110 surface. If you see from the front, you can see this is the silicon 110 surface. This is what we are interested in. Okay, that's all about the introduction of my talk. Do I need to, I got a message. The presentation mode. The main able to move my cursor. Is it okay to do like this, Dr. Chaturi? Okay, anyway, I'm going to put it present. Okay, what kind of instruments I used for this research? The main instrument I used is scanning tunneling microscopy, right? There are, first of all, this is the scanning, the figure 3A, you can see the machine that I worked. This is a UHV chamber. STM is attached to the UHV chamber. We have to maintain very low pressure inside the chamber. And on top of that, you can see there's a lead attached to the system, low energy electron diffraction. Because the main purpose of having lead on the system, because before we get the measurement in STM, so we can check the crystallinity of the surface using lead, because it takes only little time to get that thing done. So to maintain low pressure inside the UHV chamber, we have to, in this system, we have 2 ion pumps and 1 turbo pump. Then what are the main components of STM? STM includes scanning tip, that is the most important thing in this scanning tunneling microscopy, and the piezoelectric controller. And the piezoelectric controller and the distance control unit and the vibration isolation system and the computer. Because why we must have a vibrational isolation system, because during the STM measurement we have to avoid which comes to the system, because otherwise we will not be able to get the clear images. Therefore, vibration isolation system is a must. Okay. The STM do not just provide atomic resolution images of surface, but it also can act as a good spectroscopic tool. So this STM comes with the STS, the scanning tunneling spectroscopy unit, because that is very essential, because my research focus on study of electronic properties and chemical properties. To study the electronic properties, we need to have some spectroscopic data. Otherwise, it will properties. Okay. The next question: how does STM works? This is very simple process. We all know from the basic physics. The basic physics behind STM is quantum tunneling, right? So during the scanning, we have to bring the STM tip very close to the surface. Otherwise, we will not be able to get the tunneling. So this resembles the one-dimensional quantum tunneling in quantum mechanics. So here 2 diagrams you can see between the tip and the sample act as a potential barrier in quantum tunneling. If the distance or the gap between the sample and the tip is higher, then you can see this electronic wave function dies out within the potential barrier. So we won't get anything out of that. So we don't have any information out of it. Therefore, that is the main reason we have to keep the gap between the STM tip and the sample, because in the nanometer range. So when the vacuum thickness of the vacuum barrier, so it's very small, then electronic wave function can tunnel out through the barrier and we can get some information. This results tunneling current from tip to sample, or it depends on the the bias voltage that we applied in the sample and between the sample and the tip. Okay. The more about the tunneling current, because tunneling current plays very important role during the scanning process. So look at figure 5. I like this figure because this explains. You can see this happy face indicates electrons in the tip, and the sample are sitting in 2 energy valleys. But when we don't have any bias voltage, the Fermi level of the sample and the tip are in same level. So electrons in the either side don't see any empty states. So there's no tunneling between the sample and the tip. So to get the tunneling, we have to apply some bias voltage. If we apply bias voltage in this figure 6, you can see here that if we apply bias voltage to the sample with respect to the tip, the Fermi level shift. So when the Fermi level shift, the electrons in the sample side see lots of empty states. So there are lots of empty states, so they can go and occupy those places. Then the tunnel starts through the vacuum barrier. So you can see that classically it is so difficult to electrons to climb up the vacuum barrier and go in the other side. The easiest way is the tunnel out through the vacuum barrier, right? Because this is the physical phenomena behind the tunneling current. Okay. Now the next instrument that I used in this experiment is XPS. XPS is X-ray photoelectron spectroscopy. This is the system that I work. So it has X-ray source and UHV chamber. Here also we have to maintain the low pressure inside the UHV chamber, around 2 times 10 to the power minus 10 millibar, to keep the inside the vacuum chamber. The basic principle behind XPS is pretty simple. When light shines on a sample, an electron can absorb energy from the photon, and that electron can escape the material with some kinetic energy. XPS is relatively simple technique. which we can get a vast amount of information such as chemical composition and chemical states. So that is the second instrument that I used in this research. Okay, let me get back to my business now. Okay, as I mentioned earlier, I worked on silicon 110 surface. First of all, before we do anything, we have to clean the surface and we have to get the reconstructed silicon 110 surface. So I used silicon wafers. Here in the figure 8, we have to cut the sample out of this silicon wafer. That sample should be exactly matches with the sample holder which we are going to put inside the vacuum chamber. Okay, normal sample size length 15 to 10 to 15 millimeters, and sample width 4 to 5 millimeters. So this silicon wafer comes with the oxide layer on top of it. So we have to remove the oxide layer. How can we remove the oxide layer? We have to flash anneal the sample. Normally during the flash annealing, we heat the sample almost at 1200 degrees Celsius. Otherwise, we will not be able to remove this oxide layer from the sample. Once we remove the oxide layer, we can see the atoms, the silicon atoms. So after flash annealing, this is what it looks like, but still we did not get the reconstructed structure of silicon 110, because you can see this is kind of a disordered form of silicon 110. There are lots of step edges on the surface. So, and also you can see in the second image, you can see some high resolution image, you can see small spheres. Those are silicon atoms. But this is not what we want, because we want the silicon 110 reconstructed structure. So what we, okay, actually just after flash annealing, I annealed the surface to get the reconstructed surface. We have to follow the post annealing. In this image, I annealed the sample at 800 degrees Celsius. So because this silicon 110 surface extremely sensitive to temperature. So we have to hit the correct temperature to get the reconstructed structure. So in this figure, you can see that this is the reconstructed silicon 110 surface. You can see this arrow shows you the high symmetry direction on the surface. You can see this zigzag reconstructed surface. It has a well-known structure we call 16:2 structure, like silicon 111 has root 7/7 structure. Silicon well-accepted structure for silicon reconstructed 110 surface is silicon 16:2 structure. But still we are not sure about we got this reconstructed surface until we perform electronic property studies. So we have to do electronic properties studies, otherwise we cannot predict that we have the correct reconstructed surface. So to get the electronic properties, we have to collect STS, scanning tunneling spectroscopic data. Using scanning tunneling spectroscopic data, we can this is a silicon 110 reconstructed surface or not. So what we did was we plot LDOS. LDOS stands for local density of states. Local density of states, that is the derivative of tunneling current with respect to the bias voltage, and divided by absolute value of conductance. So you can see this figure 11. This is the Fermi level, right? Below the Fermi level and above the Fermi level, surface states, right? So the surface state S1 is the non-surface state for silicon 110 reconstructed structure that can be attributed to the pentagon structure of the surface. What is the pentagon structure means? On silicon 110 surface, the 4 atoms and 1 atom from the top layer combines together and form pentagon-like structure. That is why we call it pentagon structure. This surface state S1 is because of the pentagon structure. and above the Fermi level, there are another two surface states, S2 and S3 below the Fermi level, that can be attributed to the step edges on the surface. And above the Fermi level, there are three surface states. I don't see that. Let me remove. Oh, how will I do that? Okay, I don't see. Okay, above the Fermi level, there are three different surface states. Those surface states can also be attributed to the pentagon 110 surface. Okay, now that is all for the cleaning part of the silicon 110. Then next step was we had to deposit iridium on the surface. We deposited quarter monolayer of iridium, and we did the post annealing after that around 600 degrees Celsius. Then after scanning tunneling images, we got this. Figure A and B, you can see that the nanowires formed on the silicon surface, silicon 110 surface. The direction of the nanowires along 0, 0, 1 direction. Before we studied any physical properties or chemical properties, we did very basic thing. We did dimension analysis. So we measured the length, width, average length of a nanowire around 100 nanometers, and the average width around 22 nanometers, and average height around 1.7 nanometers. Then after that, we wanted to see that is there any relationship between the length and the width of the nanowire. To do that, we did some statistical analysis. So from the statistical analysis, we found out that there's a strong correlation between the length and the width of the nanowires, which means that the length and the width of the nanowires are physically coupled via strain and diffusion, which means that we can change the length and the width of the nanowires by providing the ideal thermodynamic environment. Okay, those are the dimension analysis of the nanowires. Then we move on to the electronic properties. So we did di over dV versus the sample bias. Then we found out that these nanowires are semiconductors. You can around the Fermi level, there's a flat region. The flat region means there's a band gap. There's an opening up a band gap. The size of the band gap is around 0.5 electron volts. Then after that, we did the LDOS analysis on nanowires as well as the terras that host these nanowires. Here, the figure 14, you can see in the black line shows you the LDOS curve for the nanowires, red line, the LDOS curve on the terras. But here, there's a difference curve of nanowire on the terras, the nanowire and on the terras. So above the Fermi level, nanowire has well-resolved surface states. That is mainly because of the reaction between the iridium atoms and the silicon atoms, and some part came from the step edges from the surface. Then we wanted to go ahead and do some cross-section analysis. We all know that STM cannot provide the cross-section analysis of any nanostructure. So we have to use high-resolution transmission electron microscopy. In our department, we didn't have that. We had to collaborate with some other group who has TEM. So we collaborated with Oak Ridge National Lab to find out the cross-section, to study the internal structure of the nanowire. You can see in figure 16, figure A, this is the nanowire. It's a whitish color, one is the nanowire. There's a special property of this nanowire. You can see that during the formation of the nanowire, part of the nanowire embedded into the bulk silicon, right? This kind of growth we call endotaxial growth, right? If there are two types of growth for nanostructures, one is endotaxial growth, the other one is epitaxial growth, which is formed on the surface. But this nanowire embedded, some part of the nanowire embedded into the bulk silicon, that is that kind of growth, we wanted to analyze the crystal structure of the nanowire. So we got some high resolution images. You can see these arrows shows the high symmetry direction on the surface on the bulk silicon. But this cut is perpendicular to the nanowire. You are looking one plane, right? That is why you see this in the hexagon structure, because one plane has a hexagon structure. So we are looking now on one plane. That is the perpendicular cut to the nanowires. Then the close to the bulk silicon, we identified some ordered structure of the nanowire. So we wanted to see what kind of iridium and silicon combination. And we measured the interplane distances between the interatomic atoms. So we found out that this iridium combination is iridium disilicide. Iridium, and there are different phases of iridium silicide, IRSI, IRSI2, IRSI3. Among these iridium and silicon combination, we found out that this order structure, which is close to the bulk silicon, formed from iridium disilicide, which is a semiconductor. It shows the semiconductor properties. Then after this, we wanted to get the longer nanowire. At least we wanted to make it longer to up to micron level. So we changed the annealing temperature, we changed the annealing time, we did lots of things, but we couldn't get the elongated nanowire, the long nanowires. So then finally we tried the coverage, how coverage effect on the surface. So that is how we landed on the quantum dots. So what we did was, before I explain that part, I would like to explain a little bit of quantum dots. There are lots of applications of quantum dots in transistors, LEDs, medical imaging, and solar cells, and quantum computing. So what are quantum dots? Quantum dot can be a metal or a semiconductor. If we have metal, a semiconductor quantum dot, the energy spectrum of the quantum dot is discrete. But in metallic quantum dot, electrons have relatively high density, large effective mass, and a special thing is this effect, right? That is how we identified this quantum dot is metallic or the semiconductor. Okay, so we had to follow the same procedure all the way up to the getting the clean silicon 110 structure. Then after that, we deposited 2 monolayers of iridium, and we did scanning STM images. So instead of seeing the longer nanowires, what we saw was we saw flat terraces covers the surface. But these flat terraces are not atomically flat. Okay, when we closely look at the terraces, we saw these terraces covers with quasi-periodic quantum dots. You can see in figure 20, A and B, high symmetry direction on the surface. This is quasi-periodic because this is periodic, but there's no order. That's why we call it quasi-periodic quantum dots. Okay. Before we do anything like nanowires, what we did was we just analyzed the dimensions of the nanowire along the high symmetry direction, along 001 direction, the distance between the quantum dots around 1.5 nanometers, and around 1 nanometer. Am I running out of time? Yes. And the size of the quantum dots was around 0.8 nanometers. Then we observe 2 important physical properties from the quantum dots. The first one is the Coulomb blockade. The second one is the negative differential resistance at room temperature. What is Coulomb? When the island becomes so small, this charging effect plays an important role. So during the tunneling spectrum, whatever the electrons come out from the tip will not be able to create the tunneling current, because the island is also charged, electron has also charged. Therefore, there's a Coulomb Coulomb repulsion between them. Here you can see this is the tip, this is the tunneling the quantum dot, and this is the iridium sample with iridium layer. Okay, so we have to supply some amount of activation energy to overcome the Coulomb force. So that is we call the charging energy. So you can calculate the charging energy from the basic electromagnetism. The charging energy is equal because charge is quantized, right? Because charge is quantized, so you can calculate the charging energy using this n squared. N is the quantum number of the, because charge is quantized, there's a quantum number. To observe the Coulomb blockade, there are two requirements. One is the resistance requirement, the other one is the capacitance requirements. The resistance should be and the capacitance of the charging island should be less than E squared over 2 kT. E means electronic charge, K is the Boltzmann constant. We did all this experiment under room temperature. T should be room temperature. And next we studied the physical property. Here you can see IV curves on both terrace and the quantum dots. So around the Fermi level, you can see that there's a non-zero conductance. Non-zero conductance is a well-known signature for this terrace and the quantum dots shows the metallic properties. Above the Fermi level, you can see there's a negative differential resistance. When we analyze the dI over dV was sample bias, you can see figure D shows the suppressed conductance around the Fermi level. That for Coulomb blockade. Right? So we measured the gap, this Coulomb gap. Actually, this resembles the opening up a band gap of a semiconductor around the Fermi level. This is the similar thing. This is open up a Coulomb gap. This Coulomb gap was around 0.7 volts. I think I almost ran out the time. So that is the physical properties of the quantum dots. So we did some chemical properties also. I'm not going to explain those things because I need lots of time to explain those things. So I'm going to stop here at physical properties of quantum dots. If you have any questions, you can ask me now. And I'm not going to say that I'm not going to tell about the conclusion. Actually, conclusion mainly I use clean silicon 110, which has a structure of 16/2. That's a great template to blow nanostructures. In this experiment, I use STM, XPS, and TEM to study the chemical properties, electronic properties, and the cross-sectional. Structure, we have to anneal the surface at lower temperature after the flash annealing. High resolution images shows that the low coverage of iridium tends to grow nanowires on the surface. This kind of growth we call endotaxial growth. And if we increase the coverage up to 2 monolayers, we found there's a quantum dots on the surface, quasi-periodic quantum dots. And STS measurement on both terrace and the quantum dots, they indicated that quantum dot shows metallic properties with the Coulomb gap for the quantum dots around 0.7 electron volts. Okay. Thank you very much. So if you have any questions.
Dr. Mohottige.
Yes.
Questions, any questions? It's open for the discussion of this topic. And if you have any question, you can ask.
Sorry about that. I had to rush everything because I had to explain everything very fast because of the time restriction.
There's a question from Dulanjani. Does
Yes.
this assembly show considerable reproducible properties?
Yes. This is the this self-assembly process, because first of all we have to find the proper recipe. Actually, this recipe also depend on the system that we use. So it also depend on the environment, the vacuum pressure inside the chamber. So we reproduced lots of times. We managed to get the same structure using this self-assembly process. Yes, this is a reproducible process.
So I have one question, but it's very basic one. Why we
Yes.
use silicon 110, and what are the other surface that we can use?
Yes, silicon 110 is specifically, it shows a high anisotropy, which means, so if we grow some nanostructure, we can grow those nanostructures along the same direction. That is the property we need to get when we apply this technique in the electronic device application, especially IR detect application and IC integrated circuits. The other two surfaces, silicon 1 and silicon 001, has 4-fold symmetry. So we will not get the same direction. If we formed any nanostructures, we will not get the same direction. So we might get random directions. So that is the main purpose. We use silicon 110 surface, because it shows high anisotropy.
Thank you. Any other questions?
Dr. Rasika, you
Yes.
mentioned that when you do a first cleaning process, which you are heating it to 1,200 degrees.
Yes.
And then there's I believe there's a second heating process for 800.
Yes. To get the reconstructed surface. Yes.
So for reconstruction, do you cool it first, that sample?
Yes.
Or
Yes. We have to cool the sample for at least 20 minutes. Okay. So then we need to follow the post-annealing process. Yes. So that's a very good question. I forgot it.
Any more questions?
I think there is another question from Dulanjali. She is asking, can any other material like structure can assemble on this substrate?
Yes. There are lots of research for self-assembly process. Platinum silicide, gold silicide, iron silicide. So the main reason behind the Schottky barrier are a little higher on those metals, but iridium silicide shows the lowest Schottky barriers for holes. So the Schottky barriers for other metals like platinum, gold, it's around 0.3 electron volts. And for this iridium silicide, it's very special, because the Schottky barrier for holes is less. It's around 0.17 electron volts, which is very suitable for IR detectors, because we have to get the cutoff wavelength higher.
Any more questions?
No, we cannot. We cannot. The system that we had, we cannot observe any plasmonic properties using STM. No, we have to have some higher temperatures to see the plasmonic properties. The system that we had, no.
Any questions? So
there's another question, Hiran Dhanavardhana. I mean silicon. The main reason, because to get the STM images, the sample has to be conductive. This is not like SEM. So because we are dealing with tunneling current. So therefore, sample has to be conductive. Otherwise, we will not be able to get the STM images. If you do you know what is the band gap of the silicon dioxide? I think it should be higher. I don't think we can use silicon dioxide to get the STM images, because sample has to be conductive. Otherwise, we will not get the tunneling current.
Any more questions? If no more question, I would like to invite Dr. Vasantiti Silva, Joint Secretary of IPSL, to give a vote of thanks. Dr. Vasanti, over to you.
Yeah. It was Dr. Gayan.
Dr. Vasanti.
Yeah, Dr. Gayan. Yeah.
Thank you, Professor Shant and Dr. Vasanti. Today's guest speaker, Dr. Rasika N Mohottige, and ladies and gentlemen, I'm honored to propose a vote of thanks for the IPSL monthly webinar. On behalf of IPSL, I would like to give a big thank you to Dr. Rasika for his great speech on self-assembled nanostructures. It had been a very interesting and informative speech, especially about different instruments and different theoretical explanations. It was really great. I would like to acknowledge the effort made by Dr. Chaturi and others who made this monthly webinar series a reality. Also, I would like to appreciate IPSL President all the support and the guidance provided. Finally, I extend my thanks to all the participants for being with us in this evening. I wish you all the great day and hope to meet you again in an IPSL webinar. Before winding down, I would also like to make a small request. There's a feedback form, so if possible, please fill that form also. And I wish you all the best, and thank you very much.
Thank you very much, Olu.